Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's our pleasure to have Sebastian Chiaba. Is that how you pronounce it?
That's good.
Yeah, from University of Delaware. He was brave enough to come on a holiday weekend, as we all found out after we planned his visit. But he's going to talk to us about strongly irregular graphs.
That's good.
And give a Blackboard talk.
All right. Thank you, Alexandra. So, thank you all for being here on a holiday weekend. You know, I'll try not to make it too bad, the presentation. So I will talk about a problem on connectivity of strongly irregular graphs. So just a few introductory facts. So strongly irregular graphs. So there are many strongly irregular graphs. The definition is the following. We call G, there are four parameters, V, K, lambda, mu, strongly irregular graph. And I'll just abbreviate that SRG if the following conditions are satisfied. So one, G has V vertices. Two, G is K regular. Three, any two adjacent vertices are going to have exactly lambda common neighbors. So for every U adjacent to V, the cardinality of the intersection of the neighborhood of U with the neighborhood of V is lambda. And four, the same thing. So for any two non-adjacent vertices are going to have exactly mu common neighbors. So for any U and V, U not adjacent to V and U and V are not the same, the cardinality of the intersection of these neighborhoods equals mu. Okay, so these are strongly regular graphs. Obviously, there is some relation. There are some relation between these parameters. You cannot just pick four numbers, V, K, lambda, mu, and plug them in and see if a graph with these parameters works. Some simple examples of such graphs. So I guess the most famous one is the Paley graph. So Paley graphs, here the vertices, so you take Q, a power of a prime, which is congruent to 1 mod 4. And the vertex set of the Paley graph is formed by all elements of the finite field with Q elements. And you make x adjacent to y if and only if x minus y is a square. So if and only if x minus y can be written as a square for some a in the field. So in other words, like the Paley graphs are the Cayley graphs with respect to the set of generators for this is the set of squares, if you know anything about Cayley graphs and so on. And the fact that you take Q congruent to 1 mod 4 ensures that this is actually an undirected graph. It ensures that if x is adjacent to y, then y is adjacent to x. And it's basically equivalent to saying minus 1 is a square, pretty much. And it's known that minus 1 is a square if and only if Q is congruent to 1 mod 4. But, I mean, this is an example of strongly irregular graphs. You still have to prove that. So the parameters of the Paley, so Paley of Q has the parameter. So the vertex, the number of vertices is obvious is Q. Then you have as many squares as you have non-squares, non-zero non-squares. So non-zero squares and non-zero non-squares. So the degree of regularity is Q minus 1 over 2. It takes a bit more work, but it's not very hard to prove that lambda is Q minus 5 over 4 and mu is Q minus 1 over 4. So this is a strongly regular graph with these parameters. And, I mean, this is a well-studied graph. It has all these pseudo-random properties. The eigenvalues are small, so the edges are very nicely distributed throughout the graph. Okay. So I'll give you more examples about of strongly regular graphs as we move along. I mean, I can draw, I think the smallest, maybe 4 strongly regular graph. I can draw pictures of them, and so C4. This is a 4, 2, 0, 1 strongly regular graph. C5, it's a 5, 2, 0, 1 strongly regular graph. And then you have this 3 by 3 grid where everything in the same row and the same column is adjacent to each other. So 9, 4, 1, 2, I think strongly regular graph. And Peterson graph. Is also a strongly regular graph. So this is a 10, 3, 0, 1 strongly regular graph. But again, there are many more examples. Okay, so now the problem that I'll talk about is it's about connectivity of these graphs. So the connectivity, I mean, there are many measures of connectivity for graphs. The one that I'll talk about is related to the vertex connectivity. So K of G, which is the vertex connectivity of a graph, of a connected graph G, is the minimum number of vertices in a set S. So S is a subset of vertices of the graph, such that G minus S is disconnected or a single vertex. I mean, the last condition is put, this or is just to handle the connectivity of, to give a meaning to the vertex connectivity of the complete graph. Complete graph, you cannot break it into two components. So that's the reason for the last part. But in general, so if G is connected, then this is how you define the vertex connectivity of the graph. So there is one family of strongly regular graphs which is not connected, and that consists of union of cliques. You can take a union of cliques of the same size. So if you take a union of cliques of the size, let's say k plus 1, and so on, so take as many as you want. This is going to be, it has some multiple of k plus 1 vertices, is k regular. Any two adjacent vertices, they're going to live in the same clique, so they have the same number of neighbors. Any two non-adjacent, so mu is 0. So basically, this is the only graph with mu is 0, and it's disconnected. So throughout this talk, I'm not going to, when I say strongly regular graph, I'm not going to mean these graphs which are disconnected, and their complement. Their complement is the complete multipartite graph with k plus 1 parts on each side. These are called primitive strongly regular graphs. And there's not much to talk about there about connectivity and so on. I mean, here, this is disconnected anyway. So, okay. So in 1986, Brouwer and Messner, so for all strongly regular graph except union of cliques and their complement, they proved, so if G is a vk lambda mu strongly regular graph, then the vertex connectivity of the graph equals its degree. It's obvious that this is the largest value of the vertex connectivity, as you can always delete the neighborhood of a vertex. And they also proved that the only disconnecting sets of this size, k, are of the form neighborhood of a vertex for x in V of G. So disconnecting set is a set of S whose removal disconnects your graph, breaks your graph into pieces. Okay? So no matter what parameters you give me, you give me a strongly regular graph, again, which is not a union of cliques or its complement, then the vertex connectivity is maximum, it's k, and the only disconnecting set of that size are the neighborhoods. Okay, so that's what they proved. And the thing that I like about the result is that, so this is you see it's a purely combinatorial result. Their proof makes non-trivial use of algebraic techniques. So what they use in their paper, they use Seidel's classification. So Seidel classified all strongly regular graphs with eigenvalues greater or equal to -2. So I haven't talked about what eigenvalues I mean here, but I'm going to, the eigenvalues that I'll talk here are eigenvalues of the adjacency matrix. So what Seidel did for the, he said if you give me a strongly regular graph for which all the eigenvalues of the adjacency matrix are at least -2, then your graph is one of these. There are two infinite families, and there are some kind of few other examples. So he basically classified all of them. So that's what Brouwer and Messner. I mean, if you want details about their proof, I can give it to you after the talk. But anyway, so it's a combinatorial result whose proof makes non-trivial use of spectral result of algebraic result. Okay, so in 1996, Brouwer asked the question, so what if I want the next basically disconnecting set? So all the ones of size k are neighborhoods. Now I want, tell me what's the size of the next disconnecting set. So before I tell you what he conjectures, so the picture with disconnecting sets is the following. You have a set S of vertices, and you're going to have here a subset of vertices A, and here B. Here it could be disconnected. I don't know. There could be more components, but you have no edges between these parts. So that's kind of the picture in a vertex connectivity problem. So let me denote by K2 of G. So this is going to be the minimum cardinality of a set S such that G minus S is disconnected and has every component of G minus S is not a singleton. So every component of G minus S is not a singleton. So basically here, I mean, I don't know how many. I'm going to have at least two components, but you're going to have at least one edge in each of the components. So you cannot have just a single vertex. I mean, here, if you look at this picture you have a vertex X. The disconnecting set is going to be formed by, like, S is the neighborhood of X. And then here you might have something else. You're going to have something else. Okay, so that's kind of the picture how it looks for. This would be an A and this would be a B. So that's how it looks in this situation. All clear so far? I mean, you remove these vertices, you separate X from everybody else. So it's disconnecting. And what he asked is, what if I don't want to leave just one vertex on one side? I want to have at least one edge in every component. Okay. So what he conjecture, he says show that this K2 of G equals 2K minus lambda minus 2. Now where does this number come from? Well, in a strongly regular graph, if I take an edge, I mean, he's kind of looking at the natural candidate for this disconnecting set. And the natural candidate is the following. You take an edge, and you look at all the vertices which are adjacent to at least one of the endpoints. Now, because the graph is strongly regular, you know that these two guys have exactly lambda common neighbors by the definition. And therefore, let's say this vertex is X, this vertex is Y. X is going to have K minus lambda, and minus one edge that is here, neighbors of its own. So X doesn't have anything there. And the same way, Y is going to have K minus lambda minus 1 neighbors. And maybe there's something else, something left here. So now if you look at this set, the set of vertices which are adjacent to at least X and Y and are not in X and Y, so this is kind of like an A. This is S, I guess you don't see here. So this would be S, whose size is actually 2K minus lambda minus 2. And I don't know, there's some edges here, and I don't know what could be in B. So he conjectured, okay, if I want to break the graph into non-singletons, this is the best you can do. Okay, everything clear so far? If you have any questions, just stop me. So. Okay, so what we prove, and this is joint work with, so this is joint work with, so my name, Sebastian, with Jacques Coulon and Ki-Jung Kim. They're at Post-Tech in South Korea. So what we showed is that the conjecture is false in general. So there are actually graphs for which you can break them into non-singletons by removing less than what he conjectured. So I'm going to give you first we have 4 infinite families of counterexamples. I'll give you the easiest one, which might make you think, how long did Brouwer think about making such a conjecture? Because the first counterexample is really simple. So Okay, so the first counterexample to that assertion that the minimum size of a disconnecting set whose removal leaves you with non-singleton components is the following. So you take M, it's a triangular graph. So the triangular graph, so M is, let's say, an integer, I don't know, greater than, let's say, 8 or something like that. The triangular graph is just a line graph of the complete graph, Km. Now, if you're not familiar with this notation, so the vertex set of the triangular graph is just formed by pairs, x, y, x and y between 1 and m. And A is adjacent to B. These two subsets are adjacent if and only if their intersection is 1. I mean, think of this as the edges of your graph, of the complete graph, and two edges are adjacent if and only if they share one vertex. Okay. Now, why is this a strongly regular graph? Well, you can go through calculate what V is and so on. So that the triangular graph, the number of vertices is obvious, is m choose 2. Now, it's easy to see, I think, that the number of the degree is 2 times m minus 2. And then lambda, it's m minus 2. And I think mu is 4. Something like this. Let me just double check it. Yeah. I mean, you can kind of prove this stuff. It's not very complicated. Anyway, so when you plug this number into what Brouwer said, so 2k minus lambda minus 2, it's going to be 3m minus 8. So I'm not going to go do the calculation. That's what the value is. So that's the size of the neighborhood of one edge, of any edge pretty much in the triangular graph. So what we showed is that the actual value of the connectivity is 1 less. So K2 of Tm is actually 3m minus 9. And we showed the only disconnecting sets of size 3m minus 9 are of the form the neighborhood of modular permutation of your elements 1, 2, 3 up to m of 1, 2, 1, 3, and 2, 3. So I'm just abusing a bit of notation instead of making all the brackets. So I'm just going to write the subset 1, 2, 1, 2, and so on. So first of all, so here's the picture. So you have the vertex 1, 2, 1, 3, 2, 3. So here you have a triangle because any two of them share one part. And now you're going to look at, so this is kind of my set A, and now I'm going to look at the neighborhood of A. And here it's going to be something that is left, I don't know, I'll call it B. And obviously, by the definition of the neighborhood, I don't have any edges here. So how many vertices do I have here? Well, if here I will have vertices of the form, let's say, uv. Well, one of these u has to be the same as one of the numbers in here. So u has to be between 1 and 3, and v has to be between 4 and m. That's the neighborhood. And that tells you the cardinality of NA is 3m minus 9. And you actually, in order to show that, so what I'm proving here, I'm proving that this K2Tm is less than or equal than 3m minus 9. In order to show that this is actually a disconnecting set with those properties, you have to show that when I remove this set from here, I don't end up with singletons here. I don't know, it might happen. But here, what do you have? In B, you have all the vertices of, let's say, xy with 4 less than x less than y less than m. And this part is basically the same. It's isomorphic to the graph, the triangle graph Tm minus 3, which is connected anyways. Okay. Now, so again, I gave this talk about a month or so ago at the workshop in Banff, and Chris Gotzel kind of pointed out that he didn't know how much, he doubted that maybe Brouwer thought much about this problem. anyways, this example is one of the first strongly regular graphs that you think of to try it. It's pretty simple. So this gives the upper bound. How do you know this is basically the exact value? So here, again, when you're trying to prove a lower bound on this parameter, the picture for us is always the same. You have a set A such that what you have here is a connected subgraph on, let's say, at least 2 vertices. You take here the neighborhood of A, and here you take what is left, which we call B. So now what I'm trying to show is actually something, what I'm trying to show is that for any A with at least 2 vertices and at most, let's say, half of the number of vertices, which induces a connected subgraph, then the size of the neighborhood of A has to be greater or equal than whatever value you want, this 3m minus 9. So to prove something like this, in general, it's not, we didn't find it that easy. So for specific graphs like this one, you can prove it using the definition, the structure of the graph. So you split this proof into 2 cases. So the first case is if A is a clique. Now, if A is a clique in this triangular graph, then you have 2 situations. It either looks something like A looks like 1, 2, 1, 3, and 2, 3. That's one type of a clique. Or another clique would be if A is an edge, in which case you know exactly what the neighborhood is. And the other kind of a clique will be of the form 1, 2, 1, 3, 1, let's say A plus 1 or something like that. So where all the vertices share one endpoint. So in each case here, you know what the cardinality of NA is going to be. It's already done, 3m minus 9. In this situation, the cardinality of the neighborhood is it's going to be bigger. It's much bigger than 3m minus 9. You can do this combinatorially too. If your A is like this, then you know exactly what you're going to have here. It's a vertex which pairs which contain at least 1 or 2, 3 up to A plus 1, and there are many of them. So the second part of the proof is if both A and B are not cliques. So in this situation, if A and B are not cliques, it means that A is going to contain a claw, something like this, which again, without loss of generality, you can assume it's 1, 2, 1, 3, and 2, 4. And then B, it's going to contain, again, a claw here. Again, you can assume it's 5, 6, 5, 7, and 6, 8. And now, to show that, I want to show that in the neighborhood of A has at least 3m minus 9 vertices. So here, the approach is similar to, and if you're familiar with the Menger's theorem about vertex connectivity, so the vertex connectivity of a graph, to disconnect these guys from these guys, what is an obvious lower bound for that? Well, it's the maximum number of interior vertex disjoint paths that start in this set and end up in this set. So here, basically, at this point, it's combinatorial proof. So we look for many paths that go like this. So we're going to find many interior vertex disjoint paths that start at one of these vertices. And this is very easy to do. You have to play a bit with them, but you can have paths of this form. 1, 2 goes to, let's say, 1x, which goes to 5x. And here, this x is anything between 9 and m. This is a path, an example of a path. And then you can do something similar, 1, 2, 2x. And here you put 6x, same thing. And you can find more paths. At the end, you end up with at least, I think it was 4m minus 16 interior vertex disjoint paths from this set of 3 vertices and this set of 3 vertices. So if there are at least this many, it means that if NA is going to break that part from this part, it has to contain at least 1 vertex from each of these paths. So this tells me that the size of NA is at least 4m minus 16, which beats 3m minus 9 or something like that. Okay, so here it's just combinatorial, looking for paths. Okay, so I'll leave that there. Let me write the second counterexample. So the second counterexample is the following. It's called the symplectic graph. So there are two parameters, r and q. R is an integer greater or equal to 2, and q is, again, a prime power. And there is a matrix involved. So M is going to be a 2R by 2R block diagonal matrix. With a diagonal block is this one, 0, minus 1, 1, and 0. So basically for r equals 2, this is 0, minus 1, 1, 0, 0, minus 1, 1, 0, 0, and 0. This is M in that case. All right, so how do you define a graph from here? The vertex set of this graph is going to be formed by the one-dimensional subspaces of a 2R dimensional space, vector space over FQ. And so this one-dimensional, if I refer to a one-dimensional subspace by X, this is one of the elements of a basis of that subspace. So I say X is adjacent to Y if and only if the value of the following expression, X transpose M Y, is non-zero. So some people this is called the symplectic graph over FQ. Some people call the symplectic graph the complement of this one, where X transpose My equals 0. And so on. Okay? Symplectic, this expression, this form, it's called the symplectic form. I guess it appears in geometry and so on. Now, why is this a strongly regular graph? I'm not going to give you the whole proof, but it's not very complicated. So anyway, let me just write down the parameters. So the parameters of this symplectic graph 2RQ, the parameters are the following. So V, the vertices are the one-dimensional subspaces, so that's going to be Q to the 2R minus 1 divided by Q minus 1. And you can calculate K, lambda, and mu, and they're very close. K is Q to the 2R. Lambda and mu are the same, and they're Q to the 2R minus Q to the 2R minus 1. And this is not, it's just a basically inclusion, exclusion, something very simple using dimension arguments. It's not very complicated. So this is a very dense graph. I mean, here, if you think about it, here you have about Q to the 2R plus something a bit smaller, and it's very, very dense graph. So the value that Brouwer conjecture, 2k minus 2 lambda minus 2, if you plug it in, it's going to be Q to the 2R minus 1 plus Q to the 2R minus 2 minus 2. And what we proved is that the actual value of this connectivity for this graph is Q to the 2R minus 1 plus Q to the 2R minus 2 minus Q minus 1. Yes?
The first parameter is the number of vertices?
Yes.
And the second one is the number of neighbors?
Thanks. Thank you. Thanks. All right, so somebody's paying attention. That's good. Thank you. Yeah. So it's Q to the 2R minus 1. Thanks. Yeah. But, yeah, these values are the same. And so when you plug these numbers into here, yeah, if you plug these, let me see. Did I mess up another one? Yeah. 2R minus 1, 2R minus 2. Sorry about this. Also, K and lambda and mu have to be smaller than K. So. Yeah, those are the exponents, yeah. So now you plug 2K minus lambda minus 1. Yeah, that's correct. All right, so that's what we proved. So it's basically the difference. I mean, if you let your Q be big, the difference between what Brouwer conjecture and the actual value can be as large as possible. So how do you prove something like that? Well, to prove an upper bound, you have to come up with a set A, whose neighborhood has that many vertices, and whose removal of the neighborhood is going to leave you with non-singletons. So the A that we took is the following. So you take X and Y, two adjacent vertices in your graph. So X, Y in the vertex set of this graph. And then you take A to be formed, the set formed by X, Y, and everything that looks like X plus alpha Y, where alpha is an element of FQ, say non-zero. So X and Y and everything that looks like X plus Y. So this A is going to have size Q plus 1. 2 here and Q minus 1 there. And now also another important property, this is a clique. You can show that in this graph, any two, because X and Y are adjacent, X and Y are adjacent, this is going to mean that X transpose MY equals 1. And then you can use this relation to prove that if I take X, let's say X plus alpha Y transpose M times X plus beta Y, well, what's going to happen with this form, with this matrix M, every vector is perpendicular on itself. If I do X transpose MX, I get 0. So at the end, when you compute this, here this means non-zero because it's adjacent. So when you do this calculation, what is it going to be? Anyway, you show it's always non-zero, so they're always adjacent. So this is a clique of size Q plus 1. It's called, in geometry, they call it a hyperbolic line. And now you want to figure out, so this is kind of the set A, and you want to figure out how many vertices you have in here. Well, so the size of A is going to be Q plus 1. And so you can figure out what's in here by doing some inclusion and exclusion argument, which takes about 2 pages. And you can calculate that the size of NA is actually going to be what I wrote here. Or if you have friends or colleagues who are finite geometers, you can tell them about this problem. And they can tell you again that A is a hyperbolic line in this. It's called a polar space, symplectic polar space. Then the vertices in B are the ones which are orthogonal on your A with respect to this M. And now to be orthogonal here, it's enough to be orthogonal on X and Y, because then you're going to be orthogonal on every X plus Y. So the size of B is going to be basically Q to the 2R minus 2 minus 1 divided by Q minus 1. This is going to be like a 2R minus 2 dimensional space. And so you have these many, so that will make N of A to be the number of vertices of your graph minus this and minus this, which when you do the calculation gives you exactly that value. So that's that. Now, so this tells you that the cardinality of this neighborhood is at most this value. Now what you want to show is that in B, you're not going to have singletons. And that's a bit more work, which I'm not going to go into now. It's not complicated. You prove it by contradiction. You assume that you have a singleton here, and you use the fact here you have a clique. And now the one fact that you use, if you were to have a singleton here, all its neighbors would have to go here. And now what would happen? A vertex in your clique and this guy in the original graph are not adjacent. So because they're not adjacent, you know exactly the number of common neighbors. So they would have here you know exactly the number of common neighbors, and then you can do some averaging argument to show that this cannot happen. Anyway, so I'm not going to go into details of that. So that's so this is how you get an upper bound on this value of this connectivity. Now, how do you prove a lower bound? So for lower bound, if I have a set A, let's say in here, such that this induces a connected subgraph, and let's say the cardinality of A is, let's call it T, then it's actually easy to show that the neighborhood of A has to have at least 2k minus lambda minus T vertices. This is true in any strongly regular graph. So here's the picture how this works. So if you have your A here, it's connected. So you have at least, actually you have at least one edge in there. And now you're looking at the neighborhood of A. So, you could have edges here, but you're going to have edges from here. And these edges could have, these vertices could have neighbors here as well. So if I look at these two vertices which are adjacent here, the cardinality of the neighborhood of that is going to be 2k minus lambda minus 2. And in the worst situation, every vertex in here, there are t minus 2 of them, are going to be adjacent to at least one of these guys. So here, you're always going to have at least 2k minus lambda minus 2 minus t minus 2, which is exactly this one. So this is very, very simple, and you can analyze this, what happens in an inequality case. You get some constraints. So for this problem, to show that this connectivity actually equals that value, if t is less than or equal than q plus 1, then this is good enough. Because you plug it in the number, it gets you exactly what you want. Now, if t is bigger, so I'm just going to erase here. So if t is greater or equal than q plus 2, you need to do something else because this is no longer good enough. So you use eigenvalue bounds. So vertex connectivity, so there are large literature on spectral graph theory, relation between connectivity, expansion constant, and so on, and eigenvalues. Vertex connectivity, sometimes the bounds that you get are not the nicest. They're pretty messy and technical. So here's what is known, and this is result of Hammers, and I think there is another paper by Mohar and some other co-authors on the bandwidth of graphs. So people, prove the results of the following form. If you have this picture, so this is S, this is A, and this is B, and you have no edges between A and B, then you can find an upper bound on something like this. Size of A times the size of B, n minus the size of A times n is the number of vertices minus size of B, is less than or equal than something that has to do with eigenvalues of your graph. You have to basically, to get your hand on S, you have to pretty much unpack this and try to see where S lies. So for strongly regular graphs, it turns out things work out nicer. So for strongly regular graph, if you unpack this result, you get that the size of S is at least something as follows: 4 times AB mu divided by lambda minus mu square plus 4 times k minus mu, where A and B, little a is the size of A and little b is the size of B. And this mu, lambda, k are the parameters of your strongly regular graph. So that's pretty much what you get in general for any graph. And now how do you get this result? Well, if t, which was now in my case the size of A, if this is bigger than q plus 2, and I assume by contradiction that the size of S is less than what I proved, then what's going to happen? Well, I'm going to have A plus B is the number of vertices in my graph minus the size of S. But if I assume that S is less than this, then this is going to be bigger than something. And now if A is bigger than q plus 2 and A plus B is bigger than something, then the product A times B is going to be bigger than q plus 2 times something. And you plug the numbers in. It's simpler here because you see lambda and mu are the same. This is 0. Simplifies, it's pretty technical, and it goes on. And that's how you pretty much prove it. Actually, so there are two other counterexamples. I'm not going to talk about them now. There are two other counterexamples in which the connectivity and the bounded, the actual value of this connectivity and what Brouwer conjecture differ by 1. And those two graphs are induced subgraphs of this guy when q equals 2. They're called hyperbolic quadric and elliptic quadric graphs. I'm not going to talk more about them. So I want to tell you like the method about proving that the conjecture is true for some graphs. So how, what we know about other graphs. So we can show that the conjecture is true for many graphs, and the only method that we have to prove that is through this eigenvalue thing. So if you give me a strongly regular graph for which I don't know much about its parameter, its structure, I just know the parameters, you tell me the structure, then the following is the result that we have. So let me erase it here. Something of the form, if 4 times k minus 2 lambda times k minus mu is bigger than lambda minus mu square times 2k minus lambda minus 3, then the conjecture is true for that vk lambda mu. Obviously, you want your k to be strictly bigger than 2 lambda, and if lambda and mu are close enough, then that would work. So this kills many actually parameters. So this will kill Paley graphs and a bunch of other graphs. But again, like I said, for a general graph, if you give me just the parameters without telling me how is this graph constructed and so on, this is the only result that we have, and we like to extend that to do something better. And the way you get this is following pretty much the same steps here through the eigenvalues. You follow the same step. You say it's pretty much the same idea. So what else can I tell you? Again, this is where the conjecture is true. We also prove that it's true for lattice graphs, which are the graphs where it's basically an m by m. I showed you before 3 by 3, but you can do the same thing m by m. And that's the lattice graph m is just the line graph of kmm. And that's true. And there is a generalization of an extension of this graph which comes from Latin squares. They're called Latin square graphs. It's also true there. Anyways. But again, you use the structure of the graph. You don't have some general argument that can, prove it. Anyway, so what we like to do, we like to classify all the graphs that are counterexamples because it seems like they have this, so in strongly regular graphs, there are what are called geometric graphs, which obviously come from finite geometry. So that would be a step to do for us to figure out, which graphs, if there are more counterexamples. Another thing to do would be to extend this problem, to study this problem so the generalization of strongly regular graph are called, one generalization is to look at distance regular graphs. So strongly regular graphs have this regular property and they have diameter 2. So if you look at the vertex, the neighborhood, and what is left, you have something very regular. But you could have similar graph for which the diameter is bigger than 2. So those are distance regular graphs. And more general, there is a kind of a unifying concept in algebraic graph theory, which is called association schemes. Again, I'm not going to talk about that, but that would be an interesting place to study this problem. So I think I'll stop here for Friday. I think I'll try to keep it short. Thank you very much. Questions?
Not directly related, but is there a classification for which parameters there exist strongly?
That's very good. There are necessary conditions. So when like the simple thing you can get is, if I have a graph, I take a vertex, the neighborhood has size k, and then you can do some double counting of the edges in here, and you get something very easy like k times k minus lambda minus 1 equals mu times v minus k minus 1. So this is the simplest constraint. And then you can go a bit deeper into this theory, and you can look at what happens here, the adjacency matrix of the graph, which I guess I haven't defined, and the identity and the all-one matrix, they generate an algebra, which is called a Bose-Mesner algebra, the same Mesner. And you can look at what are called the principal idempotents of that, which are the projection on the eigenspaces. And you can get some constraints, more constraints on this, which are called the Krein bounds. In the literature, you can...
What were the matrices again? The identity, the adjacency,
and the all-one. So the all-one matrix. Actually, it's equivalent to... So if you look at identity A and J, whatever they generate, it's the same thing as identity A and the adjacency matrix of the complement of the graph, which is... And this, so if you look at, for example, if I look at these three matrices, they commute. So what you can do, you can diagonalize them at the same time. So you have a common basis of eigenvectors. And then you're going to have, for strongly regular graphs, you just have three eigenspaces. The one corresponding to K, which is a all-one vector pretty much. And then you have two which are orthogonal on that. And then you can take the matrices which are projections. These are the principal idempotent projection on these eigenspaces. And these are positive semi-definite matrices, and you can play a bit with it. And just from some positive semi-definite constraint, you're going to get some constraints about this. So these are called Krein bounds, and they kill off many parameters. So if you go on Andries Brouwer webpage, he has a table of kind of feasible parameters for strongly regular graphs up to 1,000 and something. So they go in groups of 50. And on that table, it's very nicely organized because it tells you if the graph exists, it gives you a list of the parameters. If the graph exists, the row is in green, and it tells you the construction, how it's good. If the graph doesn't exist, it's in all red, and it tells you what condition actually kills it. So this is kind of a trivial condition. So parameters which do not satisfy this are not going to be there. But there are parameters which do not satisfy this thing that comes from this Bose-Mesner algebra, and those are killed by what is called Krein bounds. And for many parameters for which people have proved non-existent, it's many times like an ad hoc argument. You combine some computer search with some combinatorial things and so on. So,
density of parameters asymptotically.
yeah, I don't know if there is such thing. I mean, yeah, no. That's a good question. Thanks. Any other questions? No? Maybe he had a question. But.
Questions can be around until Monday, Tuesday, or something. If you guys decide to come to work, you can always ask you more questions later on. He'll be around.